No. All right. So, okay. I'm gonna go back and talk about um strictly that stuff about universals one more time. Um, so let's see. Right. I already said most of this before. So, we have this system. Why am I now drawing on this one? Interesting. Not, well, okay. Anyway, we have this system which at one side has um, um, some kind of basic empirical statements. And that this side has like the most, or no, let me talk about the conceptual side. We have the basic concepts down here, and we have the most universal concepts up here. And I was saying last time that, like in some sense, all universal concepts are equally universal, just like all universal statements are equally universal. Um, why does it not seem that way when you have a right? Like when you have a hierarchy of species and genera, then you call the ones most universal that have the most biggest extension, right? But we're not talking about concepts that are necessarily related to each other that way at all. So, I mean, so like might have bigger extensions, might have smaller extensions, but they all divide everything into two parts. All right, sorry. I mean, this is really a side issue just because I'm worried about what most universal means. I think to understand property, you have to say that the most universal concepts are just the ones that are farthest away from the basic concepts in the system, or they're the ones that are figure in the axioms, which are the statements in the system that are farthest away from the basic statements. So, um, and the question is, um, um, so not every concept can be defined. Obviously, some concepts will have to be left undefined. And the question is which ones? And um, and Popper says, well, the empiricist project or the inductivist project, like Carnap's version, takes these to be undefined. Like that's right. It's the in Carnap's system, it's the fundamental concepts that are undefined, and then the others are defined in terms of those. And Popper says, on the other hand, the conventionalists leave these undefined and define everything else in terms of them. And I'm going to talk more about conventionalism now because there's a whole new discussion of it in the new reading. But um, so, like Popper says, this won't do because you actually can't define any universal concepts in terms of, maybe, I guess, the basic concepts I should write like singular terms. I won't be getting myself screwed up. According to the empiricists, the singular terms can't be defined. Or according to the inductivists, the singular terms can't be defined and everything else is defined in terms of them. Meaning what? Now it's less clear that it really applies to Carney. Okay, never mind. But Popper says that won't work because you can't define universal concepts in terms of singular terms. Right. And that's the thing I was talking about last time, where he says, just by pointing to this and saying this and everything else like this, I haven't defined any particular universal concepts, because there's lots of ways of deciding what's like this and what isn't. And just by pointing to one thing, I haven't chosen one. And even if I point to 100 or a million things or any finite number of things, it's still not enough and I say all these million things and everything else like them, it's still not enough to decide what I mean by everything else like them. So I still can't get a definition. And Popper says this is completely parallel to the problem with justifying universal statements using singular statements. Right, so we can't take these as undefined and use them to define everything else. And Popper says what the conventionalist does is something you could do. Right, and the way it's supposed to work, again, like the example, and this is both like the original example the conventionalists are most interested in, and I think the easiest one to understand, that if you're talking about geometry here, these universal concepts are going to be the concepts that appear in the axioms of geometry. And the axioms of geometry will, use probably in Hilbert's axiomatization, the three undefined concepts are point, line, and plane. Well, I guess there's an undefined relation between this. Yeah, I forget, you need a few more, but anyway, so you have these axioms stated in terms of these these undefined terms, and then you can prove lots of theorems, right? Like given the axioms, you can, and various definitions of, right? So you can, for example, you could define what it means for two lines to meet at a right angle. And then you can prove that if two lines both meet at a right angle with a third line, that they never meet. These two lines never intersect. Now, I mean, I'm drawing this picture, but remember, like in the axioms themselves, the terms are undefined. So, it's like whatever we mean by line and intersect and, whatever the other fundamental concepts involved here are, you can prove this about it, given what it says in the axioms. But meanwhile, we don't know what the axioms are about because the terms are undefined. So the conventionalist says, the axioms implicitly define the terms. They define them, I guess you have to say, up to an isomorphism, something like that, right? That is, whatever, if you put in for those terms, it makes the axioms true, is what those terms mean. So in particular, like, therefore, whatever theorems you can prove from those axioms must be true of, now we still don't know, we still can't say, we still have to leave them undefined. We can't say what a line is or what a point is or whatever. And right, we can't give a definition of it, but we know that the axioms are true of it. And so we know that this theorem is true of it. So we know that whatever a line is and whatever intersection is and so forth, this theorem is true. So now if someone comes along like Einstein and says, well, actually, empirically speaking, this axiom isn't true, right? Lines like this do sometimes meet far away. So the conventionalist is going to say, well, no, those aren't lines by definition. Right, and you can see it's coming back to real life arguments about physics, right? Einstein will say, well, look, measure using a laser, nothing straighter than that. And you'll find that the beams have this relationship to each other, and the conventionalists will say, well, that just means that it's not true. Laser beams don't travel along straight lines. Look, they violate this theorem. Um, so, um, so Popper says, yes, you can do that, and he's gonna gives a longer explanation of why you can do that and why you would want to do that in the new chapter. But he says, you know, don't do that. Why? Because that means your theory can't be falsified. Right? In this case, your theory of geometry can't be falsified. Um, so therefore, what's the answer? Which terms do we leave undefined? And I think the answer is Popper doesn't really care exactly which terms we leave undefined. You know, you can't define all terms, decide which ones you want to leave undefined. Um, but what matters is um, just make sure that you don't end up with a theory that can't be falsified, however you do it. And if you ask, you know, well, wait, so how do we know what those, you know, so there's somewhere in here are undefined universal terms, and we use them to define all the others. I mean, they might be way up here, but they don't have to be. So, if you say, well, okay, um, how do we know what those terms mean then? We can't define them. And doesn't that mean we don't know what any of the terms mean? So that like the implicit definition gave a kind of answer to that, right? Yeah, we do know what they mean. They mean whatever satisfies these axioms. But what does Popper have instead of that? And I think the answer is we know what they mean because we know what to do to try to falsify the theory. Right? So we've decided by the rules we've adopted, and I think, although Popper doesn't say this, it seems like they can't all be explicit. Right? Like not all the methodological rules we've adopted can be explicit. Um, but anyway, be that as it may, we've adopted certain methodological rules that tell us how to treat this theory. We've using those rules, we've like said in advance what will take to be a falsification of the theory. And then we go about using the theory the way we said we would, and that shows that we know what it means. Right? So that, in other words, its meaning is what risk we're taking in proposing it. Something like that. The empiricists wanted to say its meaning is the procedure will follow to verify it, but again, Popper says that can't be done. So, or anyway, we could agree to regard something as verifying it, but it would be a bad idea. So, the conventionalists wanted to say the meaning consists in insisting that the axioms be true. And Popper's alternative is the meaning consists in knowing what risk we're taking in proposing the theory. I mean, I think in a sense, according to all of them, like the answer to how do you know, or what does it mean to know what the undefined terms mean is that our knowing what they mean is like adopting a certain maxim for our will. It's not knowing how to exchange them with some other concepts because you can't do that everywhere. You can't define everything. Okay, are there, so that was left over from last time. Are there questions about that before I go on? I'm gonna continue talking about conventionalism right away, if so. So, right, so I'm going to make a new start in explaining what conventionalism is, which relies less on Popper's analysis. So I think Popper agrees with that and explains why it's called conventionalism. So, like, everyone agrees, or well, almost everyone anyway, or almost every modern person agrees that language is at least partly conventional, in some sense of conventional. I guess you could say Quine also disagrees with that because he thinks there couldn't be a convention. I don't know. Anyway, like, so for example, like take the word cat. Um, why does it mean what it does? It's so it's not because some intrinsic characteristic of these marks or that sound cat that this word refers to those furry creatures with pointy ears and etc. Right? It's because I mean, so when I said like every modern person, right? Like, of course, someone may say that you know the Hebrew letters with which the Bible was written are the marks that God used to create the world. And they intrinsically refer to different things, right? Or something like that. But that's not the way nowadays we usually think. Right? So we think, this word cat, like it could mean anything, but it means what it does because we agree to use it that way, and that's the convention. And if we all changed our minds and changed the agreement, it would mean something different. Right? So that's the sense in which language is obviously at least partly conventional, right? Like what things mean depends on our agreeing among ourselves. And, in this case, of course, the agreement can't be explicit. At least it couldn't have originally have been explicit, but it's definitely not explicit now either, right? But like before anyone had a language, they couldn't get together and draw up a plan to, agree on for what words will mean. So, and that's definitely not the way we learn it now either, right? So, um, but there's an implicit convention, right? So, I mean, this is similar to, and when I lecture about Hobbes, I argue that according to Hobbes, these are actually just two parts of the same thing. That it's similar to the doctrine of a social contract, even though we never wrote down this contract anywhere. We all agree to it somehow. Right. So if I say something like cats have pointy ears, I mean, this kind of statement, like this kind of natural history statement has a weird kind of status, right? Like, I mean, this is true even though perhaps not, presumably not every cat has pointy ears. uh, just like humans are bipedal is true, even though, not everyone has two legs. Um, but let's leave those considerations aside because I just want to talk about, assume this really means the cats all have pointy ears. And the question is like, what makes that true? So, um, and um, well, what makes that true is at least partly convention, right? So that then there's two ways to look at it. So one is partly conventional, where we say that, of course, what makes this true is our convention plus the way cats are. So if we don't change our convention at all, and this word still applies to cats, this sentence could become false, or maybe you should say, this sentence would be false in a possible world or something like that, where the cats don't have pointy ears. because it would still be about cats, but now it would be false because those cats don't have pointy ears, right? Uh, so, right, that's kind of the common sense way of thinking about it. I hope people agree with that. That's kind of the common sense way of thinking about it, right? But like makes this sentence true is a kind of like coming together of our convention with the actual facts about the world. So like we've agreed to call these things cats, and so for and of course we've agreed to call something pointy and so forth, right? And we've agreed to rules of syntax and all that stuff. And so, um, by virtue of that, this means something, and then you check to see whether what it means is true or not. I mean, but maybe even in the way I was describing it, you could start to hear why someone might think there's some kind of problems like with this. Like, what does it mean that we're still talking about cats? I mean, could it turn out that cats have none of the properties that we thought they did? They aren't animals, they aren't furry, they don't have pointy ears, they're spherical and shiny and right. I mean,
Some cats are shiny.
but they're not spherical.
Well,
All right, anyway. So, I mean, um, there are problems here, but I think the alternative, at least these might look like the only two alternatives, um, is probably worse. But this is the conventionalist. So that is, this view would be conventionalism about cats or about the theory of cats or something like that, right? I mean, like idealism or skepticism or relativism or whatever, conventionalism is really a name for a type of theory, and then you have to fill in what it is you're talking about. I mean, but I think you just like you could, or it seems like you could be skeptical about everything. I guess it seems like you could be conventionalist about everything. But in any case, so this view would be conventionalism about cats. I would say that when I say cats have pointy ears, I'm giving you part of the definition of the word cat. Maybe I should say it's conventionalism about this statement. I don't know. Anyway, right? The view that the truth of this depends wholly on convention would be that this is part of the definition of the word cats. Right? So although everyone agrees that convention plays some part in making this true or false, the conventionalist says that's all there is to it. That is, this is true because we agree, because that's what, at least this is the way the conventionalists will understand definitions, right? The definition is true because we've agreed that will be the definition of the word. And this is part of it. And so, like, once you've agreed that something is the definition of a word, it can't be false. Right? If I say, define a triangle as, uh, you know, plane figure enclosed by three straight lines, or however you want to define it, then there's no question about whether triangles are plane figures enclosed by three straight lines. It's true by definition. Meaning that, like, if we agree to that definition, we agree to say that. At least that about triangles, right? So so now if you understand it this way, then like if you suddenly find lots of animals that are otherwise like cats but don't have pointy ears, this tells you they're not cats. Because we agreed to only call cats things that have pointy ears. So, I mean, So this is, like I said, conventionalism about the theory of cats or something like that. But usually what we usually people are thinking about when they talk about conventionalism is the view that so-called laws of nature, meaning both geometrical laws. I mean, of course, it's not controversial. It's not uncontroversial to call geometrical laws laws of nature at all, but that meaning both geometrical laws and physical laws and maybe some other kinds of laws that um, that those are nothing but conventions. So they so they record nothing but our agreement about how to use certain words, like point, line, force, acceleration, etc. Um, So, and it gets its start from, so let's go back to so you might say, um, so, well, maybe I should do both. Right, but replace this word, this statement here, cats have pointy ears, by line is the shortest path between 2 points. So, like, you might not start off by saying, uh, I mean, of course, it's conventional that we call lines lines. We could call them something else, like cats, right? If we agreed to change our language. And in that sense, the truth of this statement, let's say it's true, um, is partly due to convention, but it's not wholly due to convention, right? Like it's due to the convention of what these things mean, plus what we actually observe about lines, right? So, I mean, compare the line between these 2 points. And here line means straight line. I mean, I guess that's how we usually use the word line now. That historically speaking, that's not always true, right? If you look at people, but like even in the 19th century, you see them talking about straight and curved lines. But anyway, all right. So like we compare the line to other ways of getting between the 2 points, and sure enough, the line is always shorter. And of course, we haven't compared every other path, just like we haven't examined every cat, but inductively, blah blah blah, something. Right. Um, but the conventionalists get started with a question like this, like, okay, how do we know this is a lie? Or and how do we know it's shorter than this path? So, like, to tell both that it's a line and how long it is, you have to measure it with a ruler. So you use a ruler to measure this, and then of course it's hard to use a ruler to measure this, but maybe you can pull it, straighten it out, or something, right? Or you can kind of use the ruler for tiny segments of it. Take the limit, whatever. The ways, I mean, the ways we actually measure things, they ultimately evolve with us. Um, so, um, the question is, how do we know the ruler is straight and it always stays the same length? Right? I mean, maybe this ruler is actually curved, or maybe when I move the ruler from here to here, it gets shorter. Like, how do we check that that's not happening? And basically, the way we check that that's not happening is to use the fact that a line is the shortest distance between 2 points. Um, or at least that's part of what we need to check it. Right, I mean, that is like to check that the ruler is straight. We somehow find the shortest distance between 2 points, like shoot a light ray between them or something. And then we make sure that the ruler also says that this is the shortest distance. And if it doesn't, we know the ruler is either curved or it's changing its length. And of course, real rulers are not absolutely straight and they do change their length, right? So, um, really, we're relying on the fact that the ruler approximately shows that this is true. To conclude, so to speak, but what kind of conclusion is this? To conclude that the ruler is straight and doesn't change its length. So, um, um, right, so this is, I didn't write down the page number. I don't know why I didn't, but it's in the first part of this chapter. Yeah, here we go. So it's on page 58. According to this conventionalist point of view, laws of nature are not falsifiable by observation, for they are needed to determine what an observation, and more especially what a scientific measurement is. It is these laws laid down by us which form the indispensable basis for the regulation of our clocks and the correction of our so-called rigid measuring rods. A clock is called accurate and a measuring rod rigid only if the movements measured with the help of these instruments satisfy the axioms of mechanics which we have decided to adopt. Or in this case, just the axioms of geometry, right? Like, again, if what we take to be a rigid, constantly absolute and straight ruler doesn't show that the line is the shortest distance between the points, then we conclude that it wasn't. No, it wasn't straight or it wasn't rigid. And similarly, so I mean, I hope you can see, like, one reason I wanted to go through it from this direction, and I think one reason Popper himself starts again and goes through it in this direction, is to see that this is not just a logical quibble about how to define terms in the axioms. There's like a real puzzle here. Like, what's the start of geometrical measurements? What comes first? Would it really be possible to find by measuring that a line is at the shortest distance between 2 points? And I mean, this came to a head when, in effect, Einstein claimed to have discovered by measuring that the axioms of geometry or the axioms of Euclidean geometry don't apply to the real world. So this guy Dingler, who Popper talks about, wrote this book called I think the word in German is Zusammenbruch, I mean, it means like breaking together. I think it means like collapse, right? Like the collapse of science. Where his claim was that this is just Einstein has like pulled the wool over everyone's eyes and like um, they're all confused about this, and this is the destruction of empirical science, right? Because the truth and constancy of the laws of science rely on remembering that they're just conventions. Right. Right. So it comes up in the case of geometry, but it also comes up in the case of like what's more, I don't know, more clearly a part of physics. Like, right. So um, usual case, which I think I've mentioned before, is the case of um, like if you replace this with um, like a body accelerates in proportion to the force it's subjected to, or like one corollary of this is a body in motion remains in motion until acted on by an outside force, right? That is, the acceleration will be zero if there's no force. So it'll just keep moving in the same direction at the same speed. And right, so like this is obviously one of the basic laws of Newtonian mechanics. And um, again, at first you might think, well, of course, yeah, it's partly conventional, right? I mean, we didn't have to call force F, could have called it G. There's a whole weird thing about mathematical notation. Because actually everyone would be totally confused if you ever decide to call the force G, A, or whatever. It's not really arbitrary, but anyway, never mind. It's not really arbitrary, presumably because of some deeper convention or something like that. Not because God used the word F to create force when he made the world. Right. So, right. So, uh, so you might think, yeah, of course it's conventional. We call force this, we write multiplication this way, and so forth. But I mean, but it's that's not all it takes to make it true. It's true because you can measure, like, I mean, in simple case, you can see things tend to remain in motion if no force acts on them. Tend to remain in motion at the same in the same direction at the same speed if no force is acting on. And this was like an important discovery of Newton's, right? Like before, well, or I guess of Galileo's. But anyway, that that before that, it seemed like a mystery. And like people in the late Middle Ages, and Kuhn is going to talk about this somewhat, like tie themselves in knots trying to explain why when I throw something, even after it leaves my hand, it keeps moving that way rather than falling straight down. Right? Because the natural place of heavy bodies is the center of the earth, which is the center of the universe, right? This is the natural place of heavy bodies, like bodies that are predominantly earth or water, whatever. And so naturally they tend to move towards this as fast as they can. They don't move towards it all the way or instantaneously, only because there's something in their way. Now, I mean, of course, Aristotle and Aristotelians know that heavy bodies don't always move down. Sometimes they move that way, and that's called a violent motion, right? As opposed to a natural motion. But the question is, like, why, once the violence stops being applied, shouldn't the thing revert to its natural motion? And people came up with all kinds of theories to try to explain that. But and the discovery is that no, there's nothing to explain. Right? It's only, things only stop moving in a straight line at a constant speed when they're acted on violently, so to speak. So I mean, of course, it's important to this theory that it's recognized that there is no center of the universe, because we saw moons going around Jupiter, and so they're not going around the sun or the earth. Right, so there is no way to hit the center, or et cetera. But, all right, never mind that. So this looks like an important discovery about the world, and it could have been false. The Aristotelians could have been right. But the question is now, okay, let's look at this more closely. How do we know that no force is acting on us? Like, you can't see forces. How do we know that no force is moving on it? Well, the way we measure forces is by measuring the acceleration of bodies that are acted on by them. So, so if it turns out, and on the other hand, how do we know it's not accelerating? Right, and this is important because, wait, was I talking about this in here last time, or one of my independent studies? I think it was one of the independent studies. I was talking about yeah, because we were talking about Merleau-Ponty and what he says about motion. Right, so like that, there's this debate between Leibniz and Clarke, but Clarke is speaking for Newton, right? Like Leibniz and Newton weren't on speaking terms because of the whole dispute about who invented calculus. So Clarke took up the Newton side of the debate. But right, there's this whole thing about, like trying to understand the import of this example that Newton gives, that you have a bucket and it's, tied by a string to a pole. And now, like, you want to know, is the bucket going around the pole or is the pole going around the bucket? And according to Leibniz, that question doesn't make any sense, right? Like motion always is a change in relation between two bodies. And you can only ask which one is moving relative to some third body. But Newton says, no, you can tell. Because, so if the bucket is moving around, that means the bucket is accelerating, right? That is, it's not moving in a straight line at a constant speed. The way, I don't know if people have this type of physics that you already know this, or that, right? The way it works out actually is the acceleration always points towards the center of the circle. So that every moment the velocity is bending a little bit towards the center, and that's what makes it go around a circle. Right. So if the bucket is moving around, then there's an acceleration this way on the bucket. And since there's an acceleration this way on the bucket, anything at rest in the bucket is also accelerating. And so if we have some water, like at rest here in the bottom of the bucket, so like this is what we usually say, the water is held up there by centrifugal force. But I mean, really, centrifugal force isn't a force. I mean, the force is the tension in this string that's pulling the bucket towards the pole, and that's making the bucket accelerate. The water would, left to itself, would continue in a straight line, would not accelerate, but the bucket keeps it in, and so it's always like glommed up against the bottom of the bucket. So, all right, I mean, if you didn't follow the details of that, it doesn't, but the point is that how do we know that the bucket is accelerating? Because if the bucket weren't accelerating, the bucket would be moving in a straight line at a constant speed, and there would be nothing to hold the water on the bottom of the bucket. Because the bucket and the water would both be moving in a straight line at a constant speed. So, um, just like if you're in an elevator now, Einstein's thought experiment has an elevator that's falling in a gravitational field, but suppose you're in an elevator in empty space. If the elevator is moving in a constant at at a constant speed in a single direction, like at the very first you might hit the elevator and be sped up in that direction, but after that you and the elevator are moving together, right? So um um like if you're in an airplane and the airplane is moving in a constant velocity in a single direction, and you drop your pen, it's going to fall straight down because it's moving the same way as the air. It's moving this way, the airplane moving this way, and there's no outside force acting on either of them to stop it. But let the airplane accelerate, and then all of a sudden you're pushed against your seat and the pen falls back that way. Right. So so the point is, going back to our body that's moving here, we only know it's not accelerating because we can tell that no outside force is acting on it. And we only know that no outside force is acting on it because we can tell that it's not accelerating. Um, so, um, um, so again, this starts to look like an agreement about how to use the terms force and acceleration. And it couldn't be proved false, right? No matter what this body does, like no matter what the water in this bucket does, we either say, oh, there's a new force acting on it that we didn't know about, or we say, oh, the bucket is accelerating. But we never say the bucket is accelerating even though there's no force acting on it. All right. Not everyone looks happy about that. I don't know. I tried to explain that as well as I could, but right. So again, the conventionalists, well, so again, Einstein comes along and says, this is not exactly true anymore. Why? Because like as something gets faster and faster, it gets harder and harder to accelerate it. And as it approaches the speed of light, it becomes impossible to accelerate it. So you can keep applying the same force to it, but the acceleration won't be constant. Now, I mean, there's different ways of writing what goes wrong here. Like, I mean, you could also say the mass changes as it gets faster, right? But in any case, this ends up not being true. And again, that's supposed to have been discovered. So the conventionalists again will say, no, you can't discover something like that. This is an agreement about how to use these terms. You can never discover that this is false. It's a definition. So this is why, whereas in chapter 3, Popper introduces conventionalism as a way to deal with undefined terms. And I think, that has more to do with the history of like philosophy of mathematics than it has to do with the history of physics. right? Like what Hilbert would say the terms mean in his, because in Euclid, there are definitions of point, line, and plane. And, but over a long period of time, there's various stages in that criticism of this, but people concluded that those definitions are not really any good. So, so they ended up saying, oh, I guess the axioms implicitly define the terms. So, but in chapter 4, Popper starts with the idea of conventionalism as a set of quote unquote stratagems, or I have too many consonants in that word, stratagems, not strategisms, a series of stratagems to avoid falsification. The term that's translated here as stratagem is Venrum, which literally means twist. They're like conventionalist twists to get out of falsification. And Popper keeps saying, in order to defend, quote, the classical theory of the day, or actually there's quotes in the quote. it's classical theory of the day. Right? Because what Popper is saying is whatever theory we've accepted up until now, we count as classical. And then there's always going to be a temptation to try to defend it. And inductivism encourages that temptation, because it causes us to think of our theories as things that we want to justify and defend. So whenever, but especially if it's been around for a long time, the classical theory of the day is going to be, people aren't going to want to give it up. And so when they encounter evidence that tells against it, they're going to result to these kind of like twists to get out of it. I mean, I don't really know if there's a clear example of this reaction other than the transition from Newtonian mechanics to relativity and quantum mechanics. That's a good question. I mean, I guess you could count the theory of, the transition from Ptolemaic astronomy to Copernican astronomy, the very, very long transition. Right? The thing about epicycles, if you've heard of that. But I'm not sure if that's really the same thing. Anyway, yeah, so it's not like when Popper says this, it sounds like he's thinking of lots and lots of historical examples. There's always a classical theory of the day, and people always try to defend it. And I'm not sure how many examples there actually are. But that is where people try to defend the classical theory by this kind of strategy. In any case, it's certainly salient at the time Popper is writing this book that this is an argument that's still going on. I mean, I think to some extent it's going on even now. I mean, you will still hear people say, like philosophers, or sometimes it's an argument between like particle physicists and general relativists, where the people who work on general relativity think general relativity is about the shape of space. But it's hard to combine that with quantum mechanics. And one reaction has been, well, no, just think of it as a kind of weird force and make space the same as it ever was. Space and time the same as they ever were. In other words, basically going back to a kind of version of these stratagems, the Lorentz contraction and that type of stuff. But anyway, That's on the side. At the time Popper is writing, this is very influential, and he's worried about this. I think I think, like relativity and quantum mechanics have pretty much um, triumphs. Like it's after what Kuhn would call the revolution, but it's still sufficiently fresh in everyone's mind that Popper is afraid the same thing might happen again. um, so so of course Popper can't agree to let people do this. I mean, first of all, he says he thinks you can do this. And he says that in like a strong way in this chapter. He thinks that this approach is self-contained and self-consistent. Like if you want to regard this or the axioms of Euclidean geometry or anything like that as true by convention and not accept anything as falsifying it, you can. Um, Carnap actually gives an example in one of his early papers of um, how you could refuse to accept that the earth is round by like saying that, things get smaller as they move farther away, you know, light bands and whatever, right? Like if you want, you can keep, right? Or if you want, you can keep saying that everything moves around the earth and the center of the earth is fixed. You just would have to adjust what forces you think there are, and what, etc. So, um, so Popper says, like, he doesn't think that any kind of criticism of this he doesn't use this term, but a theoretical criticism showing that it must be false is going to work. Um, but, um, as I said last time when I was explaining what he said in the last chapter, his answer is that although you can do this, you shouldn't. So he's going to introduce rules to prevent you from using these stratagems. And you should accept those rules, because if you accept those rules, then you get an activity of science that can progress and make objective statements that everyone can test and so forth. So or so like when you add those rules, when you incorporate those rules into the methodology, and like, I mean, he already said that in the first or the second chapter, I guess. It's a little bit unclear why he has to come back to make that point here. But when you incorporate those rules into the methodology and you say, like, empirical science is the activity that follows the method of falsifiability or method of attempted falsification or whatever. You are you're defining empirical science in such a way that what Newton did and what Einstein did will count as empirical science. And Dingler's criticism will not count as empirical science. or what Dingler thinks people should do instead of what Einstein did would not count as empirical science. So, right, he's drawing, so the criterion of demarcation, and remember, he is a conventionalist about that, right? That is, I mean, it's not that Popper is against conventions. He says, sure enough, what we call empirical science is something we have to agree about. And it's a stronger kind of agreement than agreeing that the word cat means cat. It's a stronger kind of agreement um, precisely because something is at stake in saying what is empirical science and what isn't. And what's at stake is whether Newton and Einstein were doing what they're supposed to do or not. Um, um, whether they really were scientists, empirical scientists. Um, so, I mean, that's still raised, there's still a puzzle left here. Like, what do we say about a case like this? Um, like, um, so you have to say that, like, even though we can't define force other than by using acceleration, uh, we did mean something by it. And it's unfair, like it's against the rules of the game to change what we mean by it just to save our theory. But like, without a definition, how do we know if we changed what we mean by it? And, which I think Popper would say what that question means is, like, what can force us to sometimes take the laws of mechanics or the axioms of geometry as the problem when things don't work out the way we expect them to? Like, what can force us to not always save those principles? And, you might think if we had a definition, it could force us, because the definition would tell us what we have to mean by it. And then it would be clear that we were just changing what we meant. But that wouldn't really work, even if we had a definition. Right? The definition wouldn't literally make us say that the laws of mechanics are false. Because we would have to have rules for applying the definition. So I think Popper's answer is nothing there's no logical or physical thing that forces us to say that the laws of geometry have been falsified or the laws of physics have been falsified in a certain case. We have to guess when the point has come where we ought to say that. And our guess could be bad. And we'll know our guess is bad, I guess, because we got stuck. It will get harder and harder to use our theory. And we won't be advancing to new theories anymore. And at some point we'll realize we shouldn't have said that. But I don't think Popper can offer anything better than that. Which is important to emphasize because sometimes it sounds like he's offering you something better. Right? Like he's offering you, you know, the conventionalist said you never have to give this up. You never can give it up. The um, the like empiricist justificationist, not a conventionalist, said, you know, you can be forced to give this up because your sense perceptions will force you. um, but Popper says that won't work. The sense perceptions will never force you. And we'll talk more about that from another point of view in the next chapter, where we talk about Fries's trilemma and what the bearing of sense impressions on sentences could possibly be. So yes, your sense perceptions will never force you. And then, so you might think, but Popper's offering an alternative. Your sense perceptions can, like, they can't force you to accept a theory, but they can force you to give it up or something like that. But I don't think Popper thinks that. So, I mean, in other words, it is all basically all conventions in some sense, right? That is, scientists have to agree with each other about what counts as an observation and what is enough evidence to reject this theory. And if they stop agreeing with each other, and Popper does say this somewhere or other, I think we're going to see this coming up, that if they should stop agreeing with each other, science would be at an end. Right? If there's really a case where the scientists just couldn't agree whether this is an observation or not, or whether there's a force here or not, or whatever, then we couldn't go on. So there really are conventions, but the good thing is the conventions are conventions about how to progress and criticize and not stay stuck where we are. Okay. So I'm going to go on to talk about something a little bit different. So are there questions about what I was just saying before I go on? Yeah.
He is anti-conventionalism regarding specific science theories, but he's pro-conventionalism regarding like his theory about the sciences.
Yeah, I mean, like, I don't know if it's right to call that conventionalism, but it involves a convention, right? I mean, he thinks this is a bad place to see conventions, but there really are conventions. And I mean, so like, yeah, one of them is about what counts as science, what the demarcation criteria should be. And so like, it's not, when I say they're conventions, they're not arbitrary conventions. There's a reason for them. But but the reason is not that if we just agree to this convention about what science is, from then on, we won't have to agree with each other about anything else. The world will tell us what to do. So like, that was the last part I was saying. Maybe I should have separated those things more clearly. That there's different places that a kind of convention or agreement or methodological rule, which is in no case are they arbitrary, but nevertheless, we don't have anything to base them on stronger than our agreement with each other. So I mean, it's a little bit, you might say he's more conventionalist than the conventionalists. Right? Like the conventionalists are, you know, think that once we agree that something is the definition, logic will force us to use it the right way. And Popper is saying, no, like whatever you adopt, you're still gonna have to agree, every time someone makes an observation report, you're gonna have to agree that that's an observation, for example. And there's no guaranteeing that will happen. I hope maybe that's a little bit clearer. I mean,
So,
all right, so let me go on to talk about the logical situation now, because this is all just kind of the buildup to, or the answer to the question, you know, how can the logical fact about the relationship between the statements in a theory and singular statements, whatever those are, the next chapter is going to be about what those are, right? But how can the logical fact, how can that by itself guarantee that the theory may sometimes be falsified? And Popper's answer is it can't, right? That is, we have to adopt these rules that prevent us from using these stratagems. Because otherwise, you know, no matter what this body does, we can always make it consistent with us. But then he says, and I should have written down a page where he says this, because there's a definite transition. I wonder if I can find it. Okay. Yeah, actually, it's the beginning of section 21 on page 64. Only in the case of systems which would be falsifiable if treated in accordance with our rules of empirical method is there any need to guard against conventionalist stratagems. Let us assume that we have successfully banned these stratagems by our rules. We may now ask for a logical characterization of such falsifiable systems, right? So what he's saying is that if you agree to play fair with your theory, and also you have to agree about what counts as an observation, but the next chapter is going to be about that. So in that case, you can say what it is about the theory that makes it falsifiable by just concentrating on, and at least in this book, he thinks of theories, I think mostly as systems of statements like sentences, right? Similar to the way Carnap thinks in this period. So, and you can check, you know, using your syntactic rules, but as he keeps saying in a footnote, Tarski a little bit later on convinced him that he should really use semantics rather than syntax. But be that as it may, you can check somehow. You have your theory written out as a bunch of axioms and definitions. And then you have the rules by which, given some stuff written down, you can write other stuff down. Right? That's what a syntactical system is like. You know, so, you know, like the kind of proofs you do in Phil 9 or in like you might do in geometry in high school or whatever, where you write each step and next to it you write why that step is okay. You know, universal generalization using, you know, 1 and 2, something like that. So, so you can like determine, so to speak, mechanically, what type of consequences this theory has. Maybe I shouldn't write it that way because it's really like one long piece of paper where you're writing your proof, you know. You can check whether, like, does this theory have the negations of possible singular statements among its consequences? I mean, or it's actually not, it's going to have with initial conditions. Right? The question is whether it's gonna have statements like somewhere amongst consequences where these are basic statements, that is like observation statements. Right, so like this means black and this means raven. Should have been better the other way around, but anyway, you know, just somehow can you derive from this theory that if A is a raven, A is black? Which is the negation of the statement, the singular statement, A is a raven and A is not black. Right. So, you know, that is, the fact that that your theory has consequences like that somewhere doesn't guarantee that your theory, will be used according to the method of empirical science, because your theory could be interpreted by a conventionalist, right, in such a way that exactly where I come into this. Well, there's different ways that we'll come into it, but like, you know, either they'll say, well, when you say, look, here's something that's a raven and is not black, then they'll say, well, hold on a second. This wasn't true. That is, the initial conditions didn't hold. Yeah, okay, no, wait, I wrote this wrong, right? So, I mean, if it has consequences like this, then it can be confronted by singular statements that falsify it. Right? That is, it implies not something is A is a raven and A is not black. But of course, to falsify the theory, you have to accept the initial conditions and the negation of what they're supposed to imply. That obviously you can't derive from the theory because that's based on observations. And again, the next chapter is going to be about that, right? That is, my theory doesn't imply that this is a piece of chalk. As Popper says, scientific theories never say anything about singulars. Although he has to admit that sometimes they include some kind of hypotheses about singulars on the side or something. But right, scientific theories never say anything about singulars. The scientific theory doesn't, like Newton's theory doesn't say an apple will hit you on the head now. Like you can't be reading a textbook of Newtonian mechanics and find a sentence says, "Watch out, Abe, an apple is about to hit you on the head." Right. So, so the theory is not going to have consequences like A is a raven. That comes from somewhere else. But the way I should have said it is this. So, like, the fact that your theory has consequences like this doesn't mean that it can actually be falsified, because in the hands of a conventionalist, when they find what looks like an instance of the opposite of this, something that's a raven and is not black, they're going to say, oh no, this observation was wrong because it contradicts the axioms, right? Because this is a consequence of the axioms. And by definition, the axioms are true. So this is true. So this must be false. And then there's different ways of explaining why it's false. It's not actually a raven, right? It actually is black, et cetera, et cetera. Or just, I don't trust that experimenter. Right. So, but if you adopt the right methodological rules, Popper says, then this is sufficient to show that the theory is falsified. Right, so in the last part of the chapter, he talks in more detail about what this relationship is between the theory and its consequences that makes it falsifiable. So, I mean, it's confusing because falsifiable is, like, in one sense, falsifiable is a characteristic of the way I use the theory, right? Like, am I using it in such a way as to be falsifiable? That is, am I following the right methodology? But in another sense, falsifiable is a logical characteristic of the theory itself, which allows me to use it that way if I want to. Right. So that's why, again, he says at the beginning of section 21 on page 64, only in the case of systems which would be falsifiable if treated in accordance with our rules of empirical method, is there any need to guard against conventionalist stratagems? So, right, so this is a theory that would be falsifiable if used in accordance with the correct method. And then we have to make sure it really will be falsifiable by ruling out the conventionalist stratagems. But again, so in the last part of the chapter, he wants to focus on just this logical situation. Like, what is it that makes the theory usable by the right method? Assuming now that we're going to adopt the right method. Right, and so, like, as I've written here, what the theory has to be such that it allows us, given certain initial conditions, to infer certain basic statements. So it has to have consequences like this, where these are basic statements. That is observable. So there's nothing new about that, but what's new is, I think, is Popper's emphasis, and I emphasized this at the beginning of talking about Popper, but that you can get confused here because now there's actually two ways that basic statements are being used. One is to figure out whether the theory is falsifiable. Does it have consequences like this? And like this means that these are possible basic statements. And if there's even one of them, it's falsifiable. Now, if there's one of them, there's going to be lots of them, precisely because the theory doesn't talk about singulars. Right? So the theory can't say, this is also related to Locke's theory of law, but never mind that. The theory can't say an apple is about to hit Abe on the head. The theory can only say, given certain initial conditions, an apple will hit someone on the head, right? And the someone is part of the initial conditions, right? So like, given that someone is standing under an apple tree and the apple comes loose, the apple is going to hit them on the head. So therefore, that will always have many possible singular instances that follow from it. If Newton is standing in an apple tree, the apple will hit him on the head. Abe is standing in an apple tree, etc. Right? So, but the point is, you only have to find one, And then you know that the theory is falsifiable. And again, these just have to be possible, right? There's no reason that these have to be initial conditions that have ever occurred. Or that this has to be an observation that's ever been made. You just have to find that there are some initial conditions that you could derive a predicted observation. But so that's one way the basic statements are being used, but the basic statements are also now going to be used to falsify the theory. Right? So the way I'm going to falsify the theory is by going out and seeing this. Here's a raven that's not black. Right? Or by standing under an apple tree and the apple falls off the apple tree, but instead of falling down, it falls up. It doesn't hit me on the head. Right? So like I have to find a falsifying instance. And Popper says he thinks it's the confusion between these two that might lead you to think that he claims a single instance is always enough to falsify a theory. Because a single possible instance is enough to show that the theory is falsifiable. But Popper says a single observed instance is not enough to falsify the theory. So, like, what has to happen here is we have a theory that we've accepted, and we accept this observation. And, right, so, like, this thing about falsifiability with a possible observation is a purely logical matter, right? Like, this is a logical relationship of the axioms in this statement. But again, like, you can mechanically derive this from those. Or you can show that in any possible model, blah, 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 something semantic. Right. So, but acceptance is not a logical notion. Right? Like there's nothing on this paper to tell you which statements have been accepted. That's a political decision, basically. Right? That is, it's something that the scientists as a whole have to agree to. Again, it's a kind of convention. They have to agree to accept this statement. First, they have to have agreed to accept this theory, because if they haven't accepted this theory, at least provisionally, they're not going to be trying to test it. Right? Remember, I pointed out that testing a theory is expensive, often. Right? So we just can't test every theory that occurs to someone. We have to decide which theories we're going to put our bets on. That's like accepting the theory. So there was a decision to accept this theory at least provisionally, and that is a theory to accept this basic statement. And the question is, what's the relationship between those political acts and the political act of abandoning the theory? That is, deciding to no longer accept it. And Popper says, this is on page 66. Special rules must be introduced which will determine under what conditions a system is to be regarded as falsified. Right? We have to think about when, given that we've accepted this, we should stop accepting the theory. We have to adopt rules. And the rule that Popper proposes is that in order to falsify the theory, we need objective evidence. So that means that, like, if one person reported this observation, and even if we say, okay, we've accepted your observation report, since other people can't duplicate it, right? It's a singular thing that only happened once. Right, so it's like me saying, I was just out in the apple orchard and an apple fell off the tree, but instead of hitting me on the head, it flew up into the sky. Yeah, right. So, I mean, one response to that would be, you're lying. Right? But but another response would be that, okay, we'll note that down as an observation. It's puzzling. But like, if no one ever sees that again, um, it shouldn't affect our acceptance of the theory. We'll just say, we don't know what you saw. Perhaps it was an error. Right? We won't say you're lying. We'll say perhaps it was an error. Right? There's a famous experiment that was supposed to detect magnetic monopoles, right? Like a particle that has only a north magnetic pole and not a south magnetic pole. So that, like, there's no reason mathematically there couldn't be things like that, just like there are particles that have only a negative electric charge and no positive charge. So someone like set up a detector with like a superconducting coil and I don't know what, and they observed one magnetic monopole, and they never observed another one, and other people with the same apparatus never observed one. The joke was that what's his name? Blanking on his name. He's the inventor of quantum electrodynamics. But anyway, like his theory, like, implies that there is one magnetic monopole somewhere. And the joke was that was it. But of course, that's not how really people took the results of that experiment. They said something went wrong, who knows what. Right? So, Popper says, should the acceptance of something that goes against this theory cause us to give the theory up? And he says, we need a falsifying hypothesis that people can check in other places at other times. So there has to be a reproducible effect. So that is, there's going to be like a kind of low-level universal statement here that's accepted. And when we accept that, it's inconsistent with this theory, so we reject the theory. So it might be something like, in Canada, all ravens are not black. Right? So now, I mean, I know it can be like this because Popper's example is there is a family of white ravens living in the zoo in New York. That's one of the examples of a falsifying hypothesis. So this is not suitable to be part of a scientific theory because it's not testable at every time and place. Right? It can only be tested in Canada. But it's not one person's observation either. Anyone who's worried about it can go to Canada, can talk to people who've been to Canada. Hey, and it's once, and eventually they'll accept it. Now, accept it doesn't mean now it's justified and we know it's true. Right? That never happens. But it means we've tested this hypothesis. So, like, apparently, it has to stop somewhere, right? Like, apparently, this low-level falsifying hypothesis itself can be falsified by a single observation, right? So, like, if someone goes to Canada and sees a black raven there, then we'll know that this hypothesis was false. So we shouldn't have accepted it. And if we can't accept it, we can't contradict this. But once this has passed sufficiently severe tests, like how severe is sufficiently severe, we have to guess. No one's gonna tell us. But once this has passed sufficiently severe tests, we'll say, okay, we've accepted this falsifying hypothesis, it's inconsistent with our theory, and so we should give up the theory. No, so I've run out of time. I think this always happens, but maybe it's not a bad thing. I was gonna try to explain that thing at the end of the chapter where there's like a circle and the events are radii of the circle and the occurrences, or maybe it's the other way around. I don't remember. And by the way, that terminology doesn't make more sense in German than it does in English. Like, you just arbitrarily call something an event and something else an occurrence. So, but I think it is actually kind of illuminating, but it would take too long to explain it since I have -1 minute yet left. So maybe I'll talk about it at the beginning next time. Anyway, I'll see you then. Thank you.